Next up, we have a short talk. We're going to just go ahead and go straight into our shorter lightning talks. So next up, we have Chuck Taylor, who's going to tell us a little bit about his light vendor recently awarded a NIAC award. Some of you may know Chuck from his previous appearances in our Surface Power telecon. I see you're here. You're unmuted. Chuck Taylor is also a PM of the VSAT solicitation. So I'm going to go ahead and let him speak. He has a pretty short talk, but interesting to hear about this project.
Okay, thanks, Wes. Andrea's put up a little artist concept, if you will. It's my only slide for the day. Lightbender is a power distribution or light distribution system rather than power generation. And what we're doing is capturing and redirecting the sun to the consumer or use point. That's a boilerplate statement that I probably don't need in this group, but in many groups you get confused with solar arrays, et cetera, et cetera. What we're basically doing is taking a Cassegrain telescope concept and following the light back through and up into a what we call a periscope. You can see in the foreground here in the southwest corner of the slide. And within that periscope, we have a Fresnel lens to pseudo-collimate the light. And then we redirect it, and that periscope can move independently of the light collector so that you can point your beam in a direction other than the sun. So that was the concept that we did for the NIAC. Our measures of merit, just like Brian gave an excellent talk earlier, power is a function of mass, stowed volume, reliability are our big concerns, and where we think we play well with some of the other contenders like a laser power beaming system. Now, when we did our NIAC proposal, we thought we had a slam dunk inside the 10-kilometer range. Our break-even point with power beaming happened at about 10 kilometers. But a funny thing called physics reached up and bit us on the ass, quite frankly. We had an error in our code. Those of you who work this in detail might know that the sun divergence angle at Earth is, about a half a degree. Well, our code only compensated for that in, if Z is your directional, the direction of the sun, only in X versus X and Y. And when we corrected our code, which we did in the first couple months of our NIAC, our results were not nearly as good. So, I came clean to Wes before this, and that's one reason you're getting the little short presentation is we're doing some redesign. We're looking at different ways. We still think we're competitive, especially on the rim of a crater. We think right now, and I emphasize the word think, we have a combination of redirection, still using our baseline Cassegrain Fresnel concept to do the final directional pointing and focusing, but we are using a more of a redirection mirror from farther away to get us close to the crater rim. And we're looking at maybe being able to produce a kilowatt at about 2.5 to 3 kilometers. So it's better than a lot of people think or thought we could do, but it's not nearly as good as we originally anticipated. And so we're in the midst of our redesign and more to come there. Now, the other big thing we believe we can help with, or that we're competing on, if you will, is mass. And so we're putting our collectors on top of 10-meter masts, and we think that our base element, which is deployed autonomously, can weigh around 200 kilograms for one of our collectors, maybe 250 kilograms when we consider the periscope in the top collector. And so we still have a nice mass advantage in terms of our collection capability. And we're also looking at autonomous deployment from a very tight package. And we're employing shape memory alloys to make our mirrors. And so our NIAC is going in two different directions. One is an acknowledgement that however you get to the moon, you're going to have to self-deploy, and you're going to have to be stowed tightly and be fairly mass efficient. The optics is obviously our second avenue of approach there, but the combination, I think, is where we're going to have benefit. So that's what I have for you today. I'm sorry for the rather brief conversation, but as you can see, we're wading through the mud of creation, or the sausage making, if you will, at this point in our project.
Well, that's what you got to do in order to get something delicious, right? You have to make the sausage. So yeah, thank you very much. I think it's interesting. You know, there is one point that I think is still important to remember in that that really nice trade chart that Brian put up. There is definitely a blurry line of where the trade-off happens for redirection, solar redirection. And one of the things that I've been curious about is, you know, that thermal gradient of going right across into the PSR is pretty tricky. So you get down into the PSR with that light, maybe you can do something with even shorter range and combining these different modalities to get it where we ultimately needs to be.
And that's what we're looking at, is we're trying to position collectors or redirectors, it might be a better way to say it now, on ridge lines 10 meters up, and then have that redirection, whether it's 2 kilometers or 4 kilometers away, positioned towards what we would call the original light bender concept, and then have the photo receive element on the actual asset in the crater. This particular artist concept, we just struggle with scale. I hope everybody understands that. You either make your elements so small in the foreground to give the illusion of distance, that nobody knows what's going on, or you blow up the foreground and it doesn't look like you're transmitting that far. But we're getting some success in that. I'd say 1 to 5 kilometer range is we think is doable, which would work pretty well in Shackleton, quite frankly. So
yeah, great, thank you. I want to make sure that we get enough time to have all of our speakers come in. So how about we can handle any questions